The Center for Applied Energy Research at the University of Kentucky and Minova partnered on a new concrete product marked by unprecedented speed and strength. The goal? Create a new kind of concrete that could save lives in damaged structures and underground mines.
The project that led to the development of this product was originally funded through National Institute of Hometown Security based in Somerset, Kentucky. Their program is directed at solving infrastructure and related issues for Department of Homeland Security.
NHS and the Department of Homeland Security, they wanted something to repair shock damaged structures. This is a tough assignment. You're adding weight to the structure, which is already damaged and weakened. So what you've done is you've created what's called a parasitic load. Whatever you're putting on there had better react very, very quickly and form strength very, very quickly.
You can think of a structure with having supportive beams where the rebar is exposed and the joints between beams and columns. You don't have time to go in and clean off a structure, wipe away debris, clean up dust. This doesn't make sense. So you need a material that sticks, adheres to pretty much anything you spray it to, and still gives you that strength, compressive, flexural strength, and integrity that you're wanting out of the concrete. And the product from this project did just that.
And they are cementitious products, which means that you just mix them with water and they set hard. They harden so quickly that not only are they set in a few minutes, they are rock hard in a few minutes. We're talking structural strength in as little as 15 minutes of hardening time, which is unheard of in the world of concrete.
So what are we trying to achieve? Fast setting strength, but also continue, we don't want it to fail catastrophically. In the case of first responders entering a building, we want some integrity beyond its low capacity, and the fibers give you that. What you're doing is you're creating a dense network of fibers. So instead of breaking concrete and having one main break, fibers allow that crack to break into a multitude of cracks. So you're dispersing that energy throughout the concrete. For a high-strength concrete, you're looking at maybe 400 to 700 psi in flexural strength testing, while the final product from this project, we were achieving 1200 psi, so tripling the capacity of its flexural strength.
You can imagine where you would have a shock damage structure or a military type application, but also, for example, in the mining environment, which Minova is, of course, very intimately associated with the mining environment.
We manufacture steel and chemical consumables for mining, tunneling, and civil engineering markets. We also make a huge array of different cementitious products, particularly in America, which are sold to the mines and used for making the mines safer and more productive.
The relationship with Nova is a great example of how we partner with companies to develop new products. Tom Roble and his group have been working with them for many years. It was a natural on this project to bring them in as a partner, as they know the application methods, they know a lot of the chemistries, what is needed to be done to make a final product that can be sold.
I've often used Tom and his colleagues as a source of expertise when it comes to fly ash. Tom thought of us and our knowledge of cement products to help to work with them to develop this product for the infrastructure project, and that's how Techcrete Fast came about.
We started out with one product and Minova's already got two out of it.
The difference between Techcrete Fast and Techcrete Fast M is that the M has been specially treated so that it's almost dust-free.
All of the mining companies that they've shown to is very happy with it. In the mining environment, when something needs to be fixed or stabilized, it's got to be done quickly. It's almost a crisis situation like a shock damaged structure.
These products are unique, not only in America, but I believe in the world too. Wherever you can see a need for structural support, effectively, immediately, these products will fit the bill.
Fast set times and extreme strength come from fly ash, a byproduct of coal combustion.
CAR has the largest program in the United States looking at the use of coal combustion gasification byproducts. These are things like fly ash. Rather than putting them in a landfill or into a pond, we try to find ways to have these used really as sustainable construction materials. They work very well as replacements for Portland cement and concrete. More recently, the work's been focused on using them to make specialty concretes, low energy cements, fast setting cements, and what are called calcium sulfoaluminate cements, which are a completely different chemistry than Portland.
Concrete typically contains crushed stone, sand, and Portland cement.
It's called a pozzolane, and what it does is it makes the concrete stronger, it makes it more durable, it makes it more resistant to certain kinds of chemical attacks. So you cannot make high-performance concrete without a pozzolane. And the #1 role of fly ash is to replace Portland cement. In my opinion, replacing Portland cement and displacing it represents the greatest engineering materials challenge of our time. Portland cement is the 3rd largest emitter of carbon dioxide on the planet. And what we're doing here with CSA, these calcium sulfoaluminate-based materials, they can be formulated by using coal combustion byproducts at a carbon emission levels 1/3 that of Portland cement. We were able to take a system that was fundamentally different from Portland and use a whole different set of chemical tools in engineering this material. Instead of forming a gel, they form an actual crystal. You can use nucleating agents, things that force the crystal to form faster. And that's one of the key things that we've done. Minova handled all the patent work. They simultaneously filed patents in London and Washington, D.C.
We need to protect our very valuable intellectual property.
This project has embodied what I love of research. You can sit down with an idea or concept and you get to follow it through. And every step poses new problems, new questions, and allows you to come up with these new answers. From concept to trial in the lab to field testing to actual product. It's pretty amazing and unique.
We're actually looking at some derivative technologies. If not this exact formulation, probably something that is the daughter or son of, or at least grandson of this. So we view this as the beginning of a fruitful, hopefully very lucrative collaboration between Minova and the University of Kentucky.